Hello all, welcome to my YouTube channel. Today we are going to explore the software development lifecycle SDLC. Please do remember this video and audio is generated by various AI tools, so you may feel some gap or some lag in the voice. Kindly excuse for the same. Kindly give your feedback in the comment section. So, software development lifecycle. This concept is absolutely essential to the software development process. Think of it as a roadmap guiding developers through every steps of building reliable, efficient, and user-friendly software. Whether you are a student, a developer, or curious about how software is made, understanding SDLC gives you a strong foundation. So let's dive into the SDLC topic and why it is so important. As I mentioned earlier, SDLC stands for Software Development Lifecycle. It is well structured and organized process that software developers follow to create high quality applications efficiently. Instead of randomly jumping into coding, SDLC helps teams to play every steps from the understanding what the user need to designing, building, testing, and finally maintaining the software. By following this cycle, developers can avoid confusion, reduce error, and deliver a product that truly meets the client's expectation. Why SDLC is so important? Because it helps software team complete project on time, within budget and fewer works. It brings structure from planning to execution, ensuring the software is built in a well organized step by step manner. Let's understand this with a simple example. Imagine you are going to construct a house. What is the first thing you do? You don't just start digging or buying bricks. First, you plan where to build, what is your budget, what kind of rooms and design you want. Only after finalizing the plan do you begin build step by step. Software development works the same way. Without SDLC, building software can become chaotic and unpredictable. But with it, we follow a clear sequence, helping us develop stable, scalable, and sustainable application. So now let's understand the key difference between the SDLC and traditional development method. Traditional development often follows a ad hoc or informal approach. Teams just jump into the coding without structured planning, documentation, or clear quality control measure. It's like building something based on sudden ideas without a proper blueprint, without records, and without checks. On the other hand, SDLC brings discipline to software development. It follows a structured process with proper planning, documentation, and quality control at every step. Why this is important? Because well-documented process allows us to trace back decision, reuse components, and fix bugs more easily in the future. SDLC not only improves the development process but also enhance the software reusability, maintainability, and overall product reliability. That's why modern development teams prefer SDLC over traditional unstructured method. Next, let's explore the different phases of SDLC. Just like constructing a building has multiple steps such as planning, laying the foundation, concreting, plastering, and finishing. Software development also follows well-defined sequence of phases. These steps help ensure that every part of the software is thoughtfully planned, properly executed, and thoroughly tested. The software development life cycle is typically divided into 7 main steps: planning, requirement analysis, design, implementation or coding, testing, deployment, and maintenance. Each of these phases plays a very important role in building reliable and high performing software. In the upcoming slides, we will take a closer look at each phase, what happens there, why it matters, and how it contributes to successful software delivery. Let's begin with the phase 1 of SDLC, which is planning. Just like a strong foundation is essential for any building, the planning phase lays the groundwork for entire software development process. In this phase, the team works together to determine several key things. What is the scope of the project? What resource do we need? What is our budget and timeline? What risk might we face along the way? The main goal is to define what we are going to build, how we are going to build, and who will be involved. This phase answers important questions like: is the project technically feasible and financially feasible? Do we have the right tool and people to complete it? What could possibly go wrong? And how can we prepare for it? With a strong and realistic plan in place, the project is much more likely to succeed on time and within budget. Now let's take the closer look at the main goals of the planning phase. Think of it as setting the blueprint of the entire project. The first and most important step is to clearly define the project scope and goals. What exactly are we trying to build and why? Next, the team performs a feasibility analysis, both technical and financial. Is it technically possible to build this software with the tools and knowledge we have? And do we have the budget to make it happen? Then comes the next task of estimating the timeline and cost. How long it will take to complete each phase? What resources like manpower, software, or infrastructure will be needed along the way? Finally, it's about assigning the roles and responsibility. Who will be the project manager? Who handle development? Who handle testing? Who handle the documentation part? Setting clear responsibilities upfront avoid confusion later and ensure the team work together efficiently right from day one. The second phase in the software development lifecycle is called requirement analysis, and it plays a crucial role. In this phase, business analyst collaborates with the key stakeholders such as client, user, and project manager to gather all the necessary information about the software needs to be do. These are broken into functional requirement, what features or action the software should perform, and non-functional requirement, how the software should behave, such as speed, security, and reliability. You can think of requirement as the backbone of the software. If they are weak or unclear, the entire system can collapse, just like building the shaky foundations. Only when the requirements are well understood and documented, developers can move forward with confidence and begin writing the code. This phase ensures that everyone is on the same page and that the final software will meet the expectations of its user. So here now we will check requirement gathering techniques. To collect accurate and complete requirements, software development and developers and business analysts use several proven techniques. One of the most common method is conducting interviews with users. Talking directly to the people who will use the software helps uncover practical needs and expectations. Another approach is using the questionnaires and surveys, especially when feedback is needed from the large group of users. These tools helps gather structured and measurable inputs. Observation is also powerful. Developers or analysts watch how users currently perform the task. This helps identify what works, what doesn't, and what can be improved through the software. Additionally, teams often review the existing system and documentation. This gives insight into current process, system limitations, and avoid repeating past mistakes. After using this technique and holding several meetings with the stakeholders, the team consolidates all findings into a final, well-documented requirement specification. This finalized requirement becomes the foundation upon which the developers will start designing and coding the software. The third phase of the software development lifecycle is the design phase. In this stage, software designers and architects create the blueprint for the system. Just like an engineer creates a blueprint before building a house, the design acts as clear guide for the developers who will be writing the code. The design phase includes creating data flow diagrams to show how data moves within the system architecture to define how components and modules will interact, user interface design to plan how user will interact with the software. This phase ensures that all technical decisions are made before coding begins, which reduce confusion and mistakes later. So remember, design is not the code itself. It is the detailed plan of how the code will be written. A strong design leads to a strong software system. So, to design stable and reliable software, designers rely on a set of structured tools called design artifacts. These artifacts help visualize how different parts of the system should behave and interact. Some of the most common design artifacts includes use case diagrams, which shows how user will interact with the system and what functions they need. Entity relationship model or ER models, which defines how data is organized and how different data entities related to each other. Data flow diagrams or DFDs. These are the map. These are to map the flow of data between processes, input and outputs. Wireframes for user interface, which provide a visual layout of what the screens or pages will looks like. By combining these tools, designers build a complete and logical blueprint of the system. And this blueprint is what guides the developers in the next phase, turning design into real functional code. The next important phase in the software development lifecycle is implementation, which is also commonly known as coding. This is the phase where the plans and design comes to life. In implementation, developers take the design documents can begin writing the actual code, turning ideas into real working software applications. They use appropriate programming languages, framework, and development tools based on the project's requirements. This phase requires skilled programmers who can understand the design, write efficient code, follow coding standard, and ensure that each feature works correctly. It's important that the code is readable, maintainable, and testable so that future updates or bug fixes can be done smoothly. Simply put, implementation is where logic became action, where blueprints became a running software project. Coding standards. Just like every profession follows a certain rules and best practices, coding also demands a set of standards and guidelines. These coding standards helps make the code more perfect, reusable, and easy to understand, not just for the original developers, but for anyone who works on it later. In many organizations, these practices follow international regulations and industry recognized norms. Here are some essential coding standards every developer should follow. Use consistent naming convention for variables, function, and files. This improves the clarity and avoid confusion. Comment your code. Explaining why a block of code exists helps others to understand the logic easily. Write modular and reusable code. This breaks your code into small pieces, small functional blocks that can be reused across the project. Ensure readability and maintainability. Format your code nearly with proper indentation and structure. By following these standards, we are only create clean code, also create a product which that's easier to test, debug, scale, and maintain. In most real world projects, it is not just one developer writing all the code. Especially in large scale application, there are multiple developers, sometimes even entire team working together on the same feature or even editing the same piece of code. Without coordination, this can quickly turn into a mess. That's where version control and collaboration tools comes in. Tools like Git and platform like GitHub are essential in the modern software development process. These tools allow developers to work on different parts of the code simultaneously, track changes, and see who made what updates, merge different versions of code without losing work, and revert to previous version if something breaks. In this video, we are just introducing the concept, but don't worry, we will cover tools like Git and GitHub in detail in a future video. Just remember, in team-based development, version control isn't optional, it is critical. The next important phase of the software development lifecycle is testing, and it plays a critical role in the success of any software project. Testing is where we check whether the software or code written by the developers actually meets the original requirements defined in earlier stage. It is not about finding bugs. It's about making sure the software functions exactly as expected. Testing verifies both correctness and the reliability of the system. By catching and fixing defect early, testing helps avoid major issues that could cost time, money, and even user trust later on. Without proper testing, even beautifully written code can lead to poor user experience, crashes, and security risk. That's why this phase is so critical. It's our final checkpoint where the software goes live. Now let's explore some of the common type of testing used in the software development lifecycle. Each type focuses on a different levels of the software, and together they ensure complete and reliable functionality. Unit testing. This is the most basic level of testing. It involves testing individual components or functions of the code, usually done by the developer. Unit testing helps ensure that each small piece of the program works as expected its own. Integration testing. Here, we combine two or more units of modules and test how they work together. This ensures that when parts of the software interact, they do so smoothly without breaking the flow. System testing. This is where we test the entire system as a whole. All components are integrated and complete software is tested end to end for functionality, performance, and compatibility. User acceptance testing. This is done from the user point of view. Stakeholders or real users test the final product to confirm whether it meets their expectation and business needs. These layers of testing work together to catch bugs early, ensure quality, and build user confidence before the software goes live. Now let's look at two primary ways testing is performed: manual testing and automation testing. Manual testing is done entirely by humans. Testers manually execute the test cases, interact with the software, and looks for bugs or unexpected behavior. This approach is ideal for exploratory testing, user interface testing, and scenarios where human intuition is valuable. It allows testers to catch things that tool might miss, such as design issues or awkward user flows. Automation testing, on the other hand, use scripts and software tools to automatically run the test cases. It's extremely useful for repetitive tasks like regression testing, where the same set of tests are run repeatedly every time the software changes. Automation saves time, increases test coverage, and is more efficient for large-scale product. In most real-world applications, both types of testing are used together, combining the power of human insight with the speed of automation. Now we are approaching the final stages of the software development lifecycle. The next phase is called deployment. Deployment happens after successful testing, once the software has been thoroughly checked for bugs, performance, and user acceptance. In this phase, software is released to the end user. This release can be done in different ways. It can be a full release, where the software is made available to user at once, or it can be done gradually using methods like rolling deployment, blue-green deployment, or canary release, especially helpful in managing risk for large systems. Proper deployment ensures that the software reaches the user in a stable and secure way. Now let's take a look at some common deployment strategies used in the real-world software project. Using the right deployment method is important, minimizing the risk and ensuring a smooth transition to production. Rolling deployment. In this method, the software is released gradually across different servers or region. If any issue occurs, the rollout can be paused or rolled back. Blue-green deployment. Here, you maintain two identical environments. One is live and other is idle. After deploying the new versions to green and testing it, traffic is switched to blue-green. Canary release. This method involves releasing the software to a small group of users first. If no issues are detected, it is then gradually rolled out to the entire user base. Each strategy has its own risk management benefit. Again, teams to choose one based on the size of the system, the criticality of the application, and how much downtime can be tolerated. Even after the software is released and deployed, the work doesn't stop. The final phase of SDLC is maintenance. In this stage, the software is continuously monitored to ensure it runs smoothly. If bugs are found, they are fixed. If performance drop, it's optimized. And if user requests changes or improvement, they are added over time. Maintenance is not just about fixing what's broken. It's also about improving, adapting, and enhancing the software to meet future needs. This phase ensures the software remains useful, secure, and relevant even as technology and the user expectations evolve. Think of it as long-term care for the system, ensuring its health and growth after launch. Now let's break down the different type of software maintenance. Maintenance is not just about fixing bugs. It includes enhancement, update, and proactive improvements. Here are the four main types. Corrective maintenance. This refers to fixing bugs or issues that are discovered after the software is deployed. It ensures that system remains functional and error-free. Adaptive maintenance. This involves modifying the software to accommodate changes in the environment, like update in the operating system, hardware, and third-party tools. Perfective maintenance. It's about enhancing the feature and performance of the software based on the user feedback or changing the business needs. Preventive maintenance. This is a proactive approach. It focuses on improving the future maintainability of the software by refactoring code, optimizing performance, and addressing potential issues before they occur. Together, this type of maintenance ensures the software remain reliable, adaptable, and valuable along after its initial release. So far, we have explored the 7 key phases of the software development lifecycle. Now, let's briefly talk about the different SDLC models that teams can follow to improve or implement the phases. Depending on the type of project, timeline, team size, and client requirement, organizations choose different models to structure their development process. Some of the most popular SDLC models include the waterfall model, the V model, the iterative model, the spiral model, and of course the widely used agile model. Each of these models follows the same SDLC phases but in slightly different ways. In upcoming videos, we will talk deeper into each topic and try to understand where and when they are used. But for now, just remember the choice of SDLC model depends on the project goal size, risk level, and flexibility. And with that, we come to the end of our video on software development lifecycle. I hope you have gained some clarity on what SDLC is, why it is important, and what the different phases are from planning to the way of maintenance. In short, SDLC provides a disciplined and structured approach to software development. By following its well-defined phase, teams can build software that is faster, better, and more reliable with fewer bugs and more confidence. If you found this video helpful, please consider liking, commenting, and subscribing to my channel for more content like this. Also, remember that I have made this video with the help of AI tools, not manually prepared one, so kindly excuse if there are any voiceover mistake or slide mistake. Thank you for watching and we will be seeing the next video.